Welcome, everyone. Thank you for joining us this morning. I'm Courtney McLaren, the Event and Alumni Relations Coordinator here at Aerospace Engineering, and I guess the coordinator behind Take a Break with AE, where we hope to give you just a little glimpse of what's happening here at the department. Today, we're going to be talking with Mike Lembeck and some of the students responsible for the CAPSat program. And like Bob, I won't pretend to know any more about CAPSat than that. So Mike, I'm going to go ahead and hand it over to you and let you give the explanations.
Well, thanks. I hope I know a little bit more than that today. And if I don't, I certainly am joined by three of my students who definitely know more than I do. Logan Power is with us from the Electrical Computer Engineering Department, as is Rick Eason. And Eric Alpine's a graduate student in aerospace engineering. And the three of them have been most instrumental in the CAPSat program, which you can see on our cover slide, deploying from the NanoRacks deployer on October 12th of this year. CAPSat, the cool, let's see if it'll change slides for me, is also known as the Cool Annealing Payload Satellite. Several years ago, it started out as a slightly different acronym with more payloads on it. As we progressed through the mission development, we decided to mitigate some risks and focus on the actual most important science, which is being done with Paul Kwiat from our physics department here at Illinois and Thomas Genuine at the University of Waterloo. And their objective is to look at the use of lasers to repair damage on crystalline structures and photodiodes that would be used for quantum communications in the future. Cosmic rays come in, upset the structure in the crystal, and cause defects, which make them less able to receive the signals that they're looking for. By hitting them with a laser for a short period of time, we heat them up, and as they cool back down or anneal, they'll drop into their original structure, repairing the defects and being able to be used for an extended period of lifetime. The Chinese developed a similar satellite a couple of years ago, but it was school bus sized. And that's because it required a lot of shielding to protect the photodiodes. What Paul and Thomas have come up with is an idea in our little CubeSat, which you can see on the left there and still in the lab. That's about the size of a loaf of bread. And by eliminating all of that shielding and the extra mass and using the lasers to repair the damage that's caused in orbit, we can actually envision using these small CubeSat-like satellites in the future for doing communication efforts. So I'd like to show you a little video that we put together of the deployment, and hopefully this will come through and be able to watch and see it. That's the last time we saw CAPSat as it left the deployer on the space station. Rick, what went through your mind when you saw CAPSat finally taking flight?
I don't know if I was necessarily thinking much of anything. It was more of just the, wow, that thing that we built here is up there, and I'm never gonna see it again. Like, bye-bye. It was a very strange. And I suspect that doesn't really go away as the programs get bigger, but it was still very cool, even on this little red box sized satellite.
How about you, Logan?
You know, I'm gonna echo Rick, actually, because I was just sort of in the moment. I was just sort of filled with this. Wow, we built that thing, and it's out there. There's pictures of it floating above the earth. Isn't that the coolest thing? That's all that was going through my head at the time. I was taken aback by just how neat it was that, something we had done, and, we poured a lot of effort into that. And it's in space.
And Eric, you're probably one of the longest running folks working on CAPSat. You were with it from the very beginning, helped us get through a couple of troubling phases and made it to the end. What do you think?
Yeah, about 5 years in and a lot of good people around CAPSat. It was nice to see it fly finally. So it was nice to see.
Yeah, so the pictures, tell the story of the CAPSat development and then our post-flight work. In the top left corner there, you can see a photo of Rick and Logan and our lab manager, Murphy Stratton, doing some testing. And you can see CAPSat's kind of aimed at a window, and that window points north to campus to the ECE building where we have our ground station antenna, which you can see Logan next to just below that picture. That antenna is on a rotator and allows us to track CAPSat as it comes across Urbana several times a day. When it does, the guys there in the upper right-hand corner can take a communications pass. Typically, CAPSat will beacon at about every 90 seconds, sending us down information about its temperatures and battery voltages and so forth. So it's quite exciting when we finally saw that first blip on the screen come across. And of course, these guys are portable in nature. Rick and Logan, I tell them stories about working in the Mission Control Center down in Houston, where everything's all static and everyone has to come there to work. Well, not anymore. Your ground control center is in your laptop. And you can see in the bottom right-hand corner, Logan's actually taking a passing CAPSat during one of our classes, right in the middle of the class, and everyone was able to walk around and see what was going on. So we have some portability there, and it's kind of fun to see that happen. Yeah, I guess there's another picture there in the upper left-hand corner. Not sure how that got in there, of Dr. Kwiat in the bow tie and suspenders right after deployment. This was about 6 o'clock in the morning on the 12th, so everybody had to get up early to make it in, and of course did well. So far, we've been successful in communicating with CAPSat. This is a first for us. We were able to take down the beacons. We were able to send up commands. Unfortunately, I don't have the picture available, but we actually sent up a picture of several of the students who worked on CAPSat over time. And Logan, you want to talk a little bit about how that picture came to be and how you got it down?
Sure. So, so the picture is of a couple of us students. It's me and Rick and our radio engineer, Elizabeth, and our software lead for CAPSat, Dylan Hammond. And we originally, we wanted to have something that was stored on the satellite so that we could test essentially high volume downlink from the satellite. So it's basically a radio communications test. And by high volume, I mean, it's a couple hundred kilobytes because our communications with the satellite is actually rather slow. It's a 9600 baud modem, which is basically, an early dial-up modem in terms of speed. So it's not
for the old
fast.
Yeah, for the old folks on here, if you remember AOL and the little modem you put your phone into, that was 9600 baud.
Yeah. So this is a rather small still file by modern standards, but it's, we wanted something to test downlink with, and rather than putting something, meaningless like a bunch of random files or bits or anything, we decided to figure out how to take a picture that we had gotten of all of us a few months prior and basically convert it down to be very small and then put it on the satellite. And so we ran that test. We were able to run that test a couple weeks ago, and the picture downlinked perfectly. Rick can talk a little bit more about that. But we have the picture. That's kind of how that came to be, just as a test, but it's also a nice thing to have because, it's a nice little pictographic representation of our accomplishments.
Hey, Rick, when you were down in Houston too, you got to send a little bit of yourself into space. You want to talk about how CAPSat went in the deployer and the things you were signing down there?
Yeah. So we delivered CAPSat to nanoracks, which you can see in one of the pictures there. They're our launch integrator. And so we deliver to them. we load CAPSat into their deployer pod, which then gets shipped off to Leidos and shipped off to the launch vehicle and launched into space. And it was really cool to I'm an undergrad, but I'm taking a business trip for the aerospace department to deliver a satellite that we built to a launch integrator. It was a very weird experience. And so we fly it down to Houston. We big Pelican case, space flight hardware, do not drop. Felt very cool walking through the airport there. And we get down to NanoRacks, and those guys are great. They're very professional. We love working with them. And the process of making sure that we definitely fit in the deployer, we slide all the way through, everything clears, lots of pictures, tons of documentation. And then they close the deployer door. And then we load CAPSat in for the last time. We slide her in and she goes all the way down, and the remove before flight pins come out, and that's it. And it was very strange because we'd done all this work, and then they said, hey, by the way, we have these, there's the deployer has access hatches on this one of the sides, and there's these cover plates, and they sign the cover plates because the deployer boxes go up and come back down. So these have cycles and cycles and cycles of different missions on them. And they were like, hey, do you guys want to sign this? So we got to sign the deployer pod that CAPSat was in, which is really cool because now every other mission that goes into that deployer is going to see that, we were here, it's the we were here, we did this, which was very, very fun.
Very cool. Yeah, so CAPSat is sort of the starting point now for what we want to do in the future. In the limited time we have today, I just wanted to take a little bit of time to give you a summary of what comes next. So one of the things we're working on is actually a sequel to CAPSat called SEEK, the Space Entanglement and Annealing Quantum Experiment. Again, this is another international collaboration. We're working with the University of Waterloo, Thomas Genowine again, Paul Kwiat, our physics department, National University of Singapore, Jet Propulsion Lab, Goddard Research Center, and a company called ADVR, which makes some of this quantum equipment. And the objective of SEEK is to fly a similar payload to the space station, where it'll be attached to several attachment points in the outside of the Bishop airlock. What's unique about this is that NanoRacks owns the Bishop airlock. It's a commercial service that they're providing for deploying CubeSats off the space station. And these attachment points have never been used yet, and they wanted sort of a set of guinea pigs to go try them out to see if they'd work. So they offered us a deal we couldn't refuse, about a quarter of the nominal cost of carrying stuff up to the space station. And we very rapidly put together this collaboration to go develop the small green box you see there at the top of the screen, which will sit on a NanoRacks plate and be attached on the outside and moved around to all 6 positions on the outside of the airlock over the course of a year. Since we have some external exposure areas and we don't really need to have solar panels because we'll get our power from the station itself, we're making that space available for other materials exposure experiments. So our aerospace engineering department will be producing some polymers that will expose on the outside of one of the panels. SpaceX has a problem with their Starlink satellites. They work really great as communication satellites, but they're also shiny objects. And those shiny objects are showing up a lot in astronomy pictures, reflecting sunlight back down to the ground. And when there's 4,000 satellites like that up there, it can really cause some problems for ground-based astronomy. So they're looking to find some coatings that will cut down on this reflection. And they want to test it in the space environment, see how they stand up against atomic oxygen and thermal cycling. So we'll be testing some of those on the outside of our box. And then finally, Microlink Devices, which is up in Niles, Illinois, one of our collaborators here in our laboratory. They have some flexible solar arrays that they'd like to test out. They're currently low TRL. They haven't flown yet, so they'd like to see how they, again, stand up to the space environment. So we have a great internal payload doing some quantum physics, a number of exposure experiments on the outside, And which makes this really challenging is we just started this a couple of weeks ago, and we have to deliver by the end of March for launch in August next year. So this is a real challenging thing. You can see Logan, of course, is involved with that, with the electronics. Chi Lim, one of our other undergrads from aerospace engineering, is working all of the system structural design and helping integrate all the various components into the box. So that makes it quite a challenge, but we have a really good team that now has some flight experience under their belt, know what they're doing, and I'm sure we'll make this a success. Our next payload is also, I think, a shining star for Mr. Alpine here. Eric is completing his master's degree, submitting his thesis within the next week or so, I suspect. And he has been leading us with the folks up at Fermi National Lab up in the Chicago area, Batavia. Fermi has a theory that says that at the center of the galaxy, where there's a concentration of a black hole and other masses, that might be a good place to look for dark matter, because the black holes will attract the dark matter in one place. And there's a potential theory that says that if you take a sterile neutrino and you allow it to decay, that's indicative of a signal from dark matter, and it will show up as a 3.5 kiloelectron-volt spike in X-ray data. So Fermi is developing the focal plane array that is quite challenging from a thermal aspect. And Eric, you want to talk a little bit about that?
Yes. Yeah. So Fermi has a very powerful X-ray detector on board. It requires to be chilled to 170 Kelvin. And so we have to use a cryocooler to do that. And so there's some thermal balance here. The cryocooler itself is like a 10-watt device, and the payload itself is a 10-watt device. And so the CONOPS really has to balance not only science, but also alignment of the radiator panels on the sides, so we can effectively remove heat from the system. So a lot of the mission analysis is tightly coupled with the thermal analysis and the power analysis for this program. So it prevents a unique chance to design a CONOPS that can satisfy that.
And Eric did a splendid job leading us through a system requirements review, a mission design review, and then just recently completed a preliminary design review of the satellite. Our sponsor up at Fermi Lab is now working on getting internal funding. Eric's funded through the next couple of semesters to do some risk mitigation testing of that thermal control system. And then Fermi is looking to take this to space within the next couple of years. I should also mention the other picture down there is Michelle Zowski. She's from the mathematics department originally, came over here as a grad student in aerospace, and has done a lot of the thermal modeling of the cryocooler with the radiator panels. So our team is probably one of the most interdisciplinary teams in the Granger College of Engineering, drawing on folks from ECE, from math, from physics, and across the campus. So we're really pleased to have that kind of diversity and inclusion in our department working those problems. The next thing that I'm going to tell you about is a mission called the Lower Atmosphere Ionosphere Coupling Experiment Follow-On. We had a mission that was funded internally called LACE previously. This work is being done with Greg Earl at Virginia Tech and Gary Swenson here in the ECE department. And it's to understand how gravity waves operate in the upper atmosphere. There's a set of photometers and another set of instruments on the front of the satellite that look at the reflected light from gravity waves in the atmosphere and can tell us a little bit about what's going on and how it impacts our weather here on the ground. The original version of LACE, unfortunately, it just has a lot of issues. Wasn't going to make it to the finish line. So we jointly decided to take a different tack and rework it into what we're calling the follow-on mission, where we'll use all of the same instruments, but put it in a bus very similar to what we're going to use for the Fermilab mission. One of our collaborators is down in Columbia, Illinois, Nanoavionics, and they're working with our students, providing internships for our students, providing mentoring on our programs, and then actual flight hardware that they've already space qualified on NASA missions. to do this world-class kind of science where we want it to be highly reliable. So LACE is headed up. Our mission manager is Isabel Anderson. They're down in the corner. She's a grad student here in aerospace engineering. And she's just getting ready to provide a system requirements review in a couple of weeks for Virginia Tech. And then she'll lead on into the spring to a preliminary design review for the follow-on mission. So we're really excited about getting a second opportunity here to make good on this mission. Within our lab, we also have a focus in research on trying to develop low-cost, high-performance equipment. CubeSats in general are lower cost, but they also suffer from some reliability issues, and generally speaking, even industry, when they build a CubeSat, are typically only 70% successful over time. So we're looking to improve the reliability, improve the performance of things, and lower the cost of them further, so that we can make opportunities like we're generating here in our lab for more students to learn on. We have two of those things we're working on right now. One is a multi-camera low-cost star tracker, where we take 4 USB cameras, more or less off the shelf, and we array them in a way that their signals can overlap each other. So we build up the signal to noise ratio using the 4 cameras to get higher precision on attitude determination. And Hongray Chow is working that as a PhD candidate, and is already done some night sky testing with some preliminary prototypes. His system will also incorporate artificial intelligence to do the pattern recognition piece of the problem. And Logan has been assisting him as an undergraduate, helping him with some of the electronics. So again, another multidisciplinary, multi-department effort going on here. The bottom piece is one of my pride and joys. Elizabeth Atkinson from the EC department has taken on the opportunity to bring down the cost of transmitting and receiving things from space. The radios we use on something like CAPSat cost $8,000 to $10,000 a piece. The radio you see there on that page, which is already on the ground, transmitted and received from each other, is about $250 worth of parts, plus Elizabeth's labor and blood, sweat, and tears. So we think we have something here that is going to significantly lower the cost of doing operations in space. And she's going to continue to work to develop that. And we've already engaged one of our distinguished professors, Bruce Conway, to take up one of the radios in an airplane and do some far field testing with it in the near future. So we're pretty excited about that. We also know that we have to kind of look backwards. Folks like Logan and Rick and Eric have to be encouraged, you know, and Isabel and Michelle and Elizabeth, they need to be encouraged to come forward to work in aerospace engineering. And so we're working in a collaboration with the university's 4-H and extension group to try to grab young people while they're still in high school and grade schools and get them intrigued with aerospace engineering and draw them into coming here to Illinois in our department. To that end, we have a program we're developing for a 1U CubeSat called the LASSI 0. You can see that in the upper left-hand corner. And Eric and Logan and Rick, of course, have their hands very dirty on this program, working to develop the requirements for it. We're bringing in outsiders to do program reviews and making sure that when we're ready to build this, it's going to be a reliable piece of hardware that we can go forward with. We're also putting together what we're calling an educational development unit, and that you can see in the center portion of the page there. Inside the plexiglass is a small 1U CubeSat demonstrator. That demonstrator can take in inputs like temperatures or the illumination on a solar array, or measure a magnetic field around it. And we first exposed this at the State Fair this year in the STEM pavilion over there. And we got a lot of good feedback to the point where our sponsor in the 4-H extension group has now asked for 12 of these units to send out to Illinois high schools and to start to try to bring in more students and working different types of payloads. We envision things from taking pictures of the Earth to germinating seed corn in space. So we're going to run a camp next summer, and hopefully out of that camp we'll find a really good payload and then try to go fly it for those high school or grade school students. Which brings us to, that's the front end, bringing the students in from high schools. They have a great career here at Illinois, And then what happens? Well, if you're in aerospace engineering, you leave the state, you go to Florida, California, Colorado, and we're trying to stop that. We'd like to keep some of these great brains here that we've collected in our state and working on that. So to that end, we've created what we've called our Illinois Small Satellite Consortium. And we have gathered up another set of small aerospace companies and government labs and folks like that to work with us in a collaborative sense, and also to provide opportunities for internships at their companies. And then, you know, try before you buy. And after you see how good our students are, you'll offer them jobs in the end. So we're working with those folks to get the consortium running. Nano Avionics, as I mentioned, has been a big partner in that. I see David Carroll on here from CU Aerospace. Dave has been a fabulous sponsor of work over here in our aerospace engineering department. Extremely grateful for the efforts he's provided us, or tasks he's provided us with. Where's the future lead then? Well, one of the things we've been doing with this consortium is working through the College of Engineering and our Legislative Affairs Office here to go talk to government officials in the state of Illinois. And what we'd like to do next is actually build some CubeSats for the state. Why does the state need a satellite? Well, there's a lot of things that the state could be helped out with if they had additional information from orbit. Things like weather damage caused by tornadoes and floods, to be able to get a quick assessment of that, to know where to send the help to. Looking at the parking lots at Walmart, counting cars there. That tells the state what kind of tax revenue they may have in the future. So it just provides a lot of data and opportunity for developing information that the state can use to work more efficiently. It keeps the jobs here in the state. There's a lot of secondary jobs that can occur as well. When you build a satellite, you get a lot of data. You've got to do something with that data. So there's a lot of software companies that can turn that data into services and products for people out in the streets. Real estate agents can use it to see where to go, you know, set up their efforts for the next development. And we're just now getting to the point of going to talk to that staff for the governor's office, and maybe set up a program that will continuously allow us to build a satellite, say every 3 years, providing opportunities for folks in our lab to continue to work on their dreams that brought them here and do good things for the planet. So that gives us a really quick short summary of what we've got on in the lab. Hope you enjoyed what you heard. I see several of our students here, some past and present, and we certainly enjoy having you folks come back and work with us as well, sitting in on design reviews, anything like that always helps. So really appreciate it. Back to you, Courtney.
All right. Does anybody have any questions?
Yeah, I have a couple. This is Rod Burton. They're referring to your satellite that just put up. I was expecting that thing to tumble as it came out. How did you prevent it from tumbling?
It had very smooth edges. So the satellite itself sits in the deployer and is pushed by a spring and a plate behind it. And so it's given a lot of linear motion coming forward. And if there's nothing that tips it off at the end, it'll just continue to go that way, very straight. So we were very fortunate that there was no tip off, no, it didn't catch an edge. It just slid out of the deployer very smoothly and went into orbit.
Thanks. Another question is, what's the typical temperature that you're measuring inside the bus on the satellite?
We're sitting right at about 23, 24 degrees C. So it's cozy room temperature.
Room temperature. Okay, thank you.
I have no question, just to say very impressive. Excuse me. Very, very impressive.
Thanks, Alan. Yeah, it's we have the best students you can possibly find here in the college, and they're doing all the work. We've built a culture now where everybody looks over each other's shoulders, assist each other, working together to do good things and reliable things as well. And I'm really proud of that, proud of the students and the efforts that they put in. For instance, I just give you one more example about Rick and Logan here. They've been getting up in the middle of the night lately because CAPSat's major passes are occurring between like 10 p.m. and 6 a.m. So they've been having to wake up rather early and at odd hours to go work at it. And that's the kind of dedication these guys have. And Eric too, just to get CAPSat to the finish line is tremendous.
Yep. On your first slide, there's an antenna. Is that the communication between Earth and space?
Yes, on CAPSat, there is something akin to a tape measure like antenna that's about 6 to 8 inches long. And it's actually held to the sides of the satellites as it slides out of the deployer. About 45 minutes later, the satellite receives a signal from the clock to wake up, and it cuts the lines, and the tape measures unfold and creates the planar antenna that we have.
I was under the impression that you need the dish to collect the signal, but apparently I was wrong.
No, down here on the ground, we actually use, I'll show you, it's a Yagi tuned for the frequency. You can see there in the lower left-hand corner, that's
Yep,
that's what we use.
cool.
Yeah, and just another quick story about these guys and the kind of effort they put in. That antenna is on the roof of the ECE building, and it has to make probably 150 foot, 200 foot run down to an office in the top of the ECE building. And when we started to look for CAPSat, we weren't hearing it. And it looked like the software we used to demodulate the signal couldn't work with all of that signal loss from the roof down to the power amplifiers. So the two gentlemen on the screen here went and scavenged a radio that we had as a spare on another satellite. And of course, hardware always looks better than software, and especially when it's the same hardware. We grabbed the radio that's identical to the one in CAPSat, and they talk symmetrically to each other. And after they put that into the system with a little baling wire and spit and chewing gum, they were able to get CAPSat talking and listening to us. So these guys are pretty innovative, and they make us all look good.
Thanks.
All right.
Proud to be an Illini.
Definitely.
All right. I think that's all we have time for today. Thank you, everybody, for joining us. If you have any more questions for Mike or his team, feel free to email Mike, or you can send them directly to me. I just want to say thank you very much to Mike, Eric, Logan, and Rick for joining us today, and for sharing all the developments you guys are working on. It's like our alums have said, it's truly incredible work. So thank you, everyone, and we hope to see you next time.